So what's included in the new version of FluidFlow 3? Well, firstly, we have the ability now to carry out auto sizing of a considerable number of components. So we can automatically size our pipes, centrifugal pumps, PD pumps, fans, compressors, rotating PD pumps, pressure control valves, flow control valves, differential pressure controllers, orifice plates, inline nozzles, and venturi tubes. And this supplements the ability in the previous version to automatically size relief valves and bursting discs. And because we can now automatically size these components, we no longer have the need or the requirement for the auto tab, which you might be familiar with at the far right hand corner of the component palette. So that auto tab has now been removed in the latest release, and you'll see that in just a moment's time. So if we look firstly at auto pipe sizing, this feature is applicable to systems where the flow rate has been specified or is a design condition. And what determines flow rate? Well, sometimes we would have a transfer time, so we might have a need to, for instance, transport 500 meters cubed of fluid from A to B in 2 hours, so that would obviously equate to 250 meters cubed per hour. Often the heating or cooling load will dictate the design mass flow rate and production rates at various facilities. When sizing pipes, we can choose from a number of different sizing models. Firstly, the economic velocity model, which you will already be familiar with in the previous versions of the program, and this model applies to liquids and gas flow systems. Secondly, then we have a design velocity model, and thirdly, a pressure gradient sizing model, and this applies to all fluid phase states, so our liquids, gases, two-phase fluids, and slurry systems. So we can also automatically size control valves, and previous editions as well, if you recall, required you to set the design flow direction for your control valve. So if you can see in the top diagram here, we've got our simple pipe system with a controller in it, and you can see on the right hand side of the control valve the little red dot which denotes the discharge side of the valve, in this case pipe reference user number -2. But we no longer need to set this flow direction, and now when you build the model it will appear like so. So you can see the red dot has been removed and the software will automatically determine the flow direction in the system. Okay. We also now have the ability to display a data report for your model. And you can do this by simply selecting View from the toolbar at the top and Data Report. And what you see is a little report like you see here on the screen. So you've got your input information on the left-hand side in green and your calculated results on the right-hand side. And you can customize the display to show either just the input information for your system, just the results for the system, or as you see here, the combined input and results information. And that applies to all pipes and all fittings in the model. Okay, and you can obviously customize the columns that appear, so you can hide some and add others. Okay. Also, we mentioned about the auto tab being removed. So if we look at the top diagram, you can see we've got the component tabs that we're all familiar with, and the auto tab is missing now from the right hand side. We have added a new components bar, which you can see at the very bottom here, and this components bar is available by selecting View and Component Bar, and this includes all components available in FluidFlow, and you can customize the display to remove or add any components you wish, and you can do so by selecting the little arrow on the right hand side here and Add or Remove buttons, and I'll give you a little look at that shortly. In relation to thick orifice plates, just be aware that we have amended or changed the calculation routines for this component, and we're using a much more robust calculation method, which is easily back-solved and allowing us to determine the auto-sizing function in the system. Okay, so that's just a little overview in PowerPoint format of the new features in the software. So let's activate the software. I'll just hide the component bar to start off with. Okay, so the auto tab's missing. Okay, so if we look at, say, for instance, sizing a pipeline, so I'll drop a known flow node onto the screen, And I'm doing this because I mentioned earlier we need to know the design flow rate, or it needs to be a design condition in the system in order to be able to size the pipeline. Okay, so let's choose a flow rate of 30 meters cubed per hour. I'll just turn on my pipe reference number and select calculate. Flow direction has been shown. The pipe by default is 10 meters in length and it's 2 inch. So if I look at my results, I can see that the calculated velocity is 3.85 meters per second, which is fairly reasonable. Let's increase the flow rate in this system. Let's make it, say, 60 meters cubed per hour. And if I look at my pipe, the sizing model I'm using now, which is a new field, is economic velocity, and I can choose by velocity or by pressure gradient. Let's choose economic velocity for the moment. So I'll recalculate to refresh my results. And you can see the end velocity in this pipeline is 7.7 meters per second, and the economic velocity value calculated by the software is 1.22, which equates to an exact pipe diameter of 131 millimeters. And obviously we have a 2-inch pipe which is only 52.5 millimeters. So straight away we can see, okay, we might need to increase this pipeline based on the suggested economic value. So let's try 132, even though it's not your standard pipe size, but let's try it and see what kind of a result we get. So I'm recalculating to refresh my results, and you can see the size now that I have entered is 132. It matches well with that suggested by the software, and the end velocity is now fallen to 1.22 meters per second, which is closely in line with 1.22. Okay, so this very quickly allows you to develop an economic system design. Okay, now obviously you can choose a database pipe size and select the next closest matching pipe diameter. Okay, so if I, for instance, select by velocity, it's going to ask me now what's the design velocity for the system, and it might be, for instance, 1.3 meters per second. So I'm going to recalculate to refresh my results. Look at my results tab, and you can see the sizing velocity that I have entered is 1.3, and that gives me an exact velocity pipe diameter of 127. Again, I had returned the pipe to the default diameter of 2 inch, so I'll change it now to something close to 127. So let's go back. And let's, for instance, let's just try 4 inch. Recalculate. And now you can see the 4 inch pipe is 102 millimeters, gives me a velocity of 2 meters per second, which is falling and getting closer to the design velocity. So again, I can come back and increase the diameter. Let's try the 5 inch pipe. I'll just look at the results tab and refresh. And now you can see 128, we're getting very close now. So the end velocity has fallen within the realms of my design criteria of 1.3 meters per second. So that's just a very quick overview of the pipe sizing feature. And obviously you can use the by pressure gradient. So you can set the pressure gradient for the pipeline. Okay? So let's look at another example where we're going to model a control valve. So I'm just going to change the inlet condition to a known pressure, and I'll set that to 1.2 atmospheres, and I'll return this to a 2 inch pipe. Refresh. Okay, so let's add a flow control device. Again, the little red dot is now removed. We don't need to assign flow direction because it's done automatically. And you'll see a new field here now, automatically size, and it's turned off by default. Okay, and the rest of the parameters that we see here are the same as what we have had on the previous versions of the software. Okay, so you can select the valve model and it brings you into the valves database. But what I'm going to do is I'm going to automatically size my valve. And now it's asking me for the design flow, and the other fields such as valve model and so on have been removed because this is an automatically sized function. We want to determine the CV or KV. Okay, so let's just use the 10 meters cubed per hour that we have here. I've recalculated, and if I look at my results, you can see the software is calculating the friction loss and also the calculated CV in gallons per minute per PSI, 28. And we can change these units to whatever units we wish. Okay, and you can change this to calculated CV. All right. Let's say, for instance, if we have an orifice plate. So I'm right-clicking on the valve, selecting Change Component, And let's try a thin, sharp-edged orifice plate. I'll go back to my Input tab, and you can see Automatically Size is turned on because I've copied this across from the previous control valve. It's asking me to size for flow, 10 meters cubed per hour. If I recalculate, it's now telling me the calculated size I need for this orifice plate, 27.8 millimeters. So a lot of the pain is taken out of the design or calculation process, simplifying the system design for us. Okay, so let's take a look at a more complex example. So I'm just deleting what we have here on the screen, and I'm going to consider modeling a cooling circuit. So here's a little back of the cigarette packet sketch. So we've got our inlet down here. We've got 15 degrees C water. We're going to have a pump, and we're going to have 4 heat exchangers in this system. So we've got 370 kilowatt for the first one, 250, 370, and 250 kilowatt for the end shell and tube heat exchanger. We're going to balance the flow distribution in this system using orifice plates. So you can see the design flow rate for this system is given here. So for the 370 kilowatt unit, we've got a design mass flow rate of 2.969 kilograms per second, and that's just been calculated from the equation Q equals MC delta T, and we're using 4154 for the specific heat of water at 30 degrees, and we're using a temperature differential of 30 degrees C. And that's because the design condition in this system is a 30 degrees C temperature change across each heat exchanger. Okay, so 2.969 for the 370 kilowatts, so you can see that matches this unit. And then 2.006 kilograms per second for the 250 kilowatt heat exchangers. And you can see a little note at the bottom that the design duty pressure rise in this instance is 2.5 bar. Okay, so we can very, very quickly set about modeling this system. So I'm just going to drop 2 known pressure nodes on my flow sheet. I'll connect up the pressure nodes with my steel pipework. And now I'm just going to add in the little lateral pipelines, which will include the heat exchangers. So let's drop our 4 heat exchangers onto the system, like so. And I'm going to have orifice plates in this system to balance the flow. And obviously, we're going to have a centrifugal pump. Okay. Now, because the auto tab is removed here, how do I size or automatically size my pumps in the system? Well, with the centrifugal pump, we've added this additional field, automatically size, so I need to turn that on. And now it's asking me to select my sizing model. And I can size the system based on the design flow rate or the duty pressure rise, the design duty pressure rise for the system, which we know in this case to be 2.5 bar. So I'm just going to select for pressure rise and 2.5 bar. Okay, the fluid is going to be water at 15 degrees C. It's at 1 atmosphere at the inlet and outlet. My heat exchangers have the amount of heat energy transferred defined in kilowatts. So let's define that fixed transfer rate into the system because we've got a cooling circuit, and we're going to define it in kilowatts. And let's just enter 370 kilowatts for all 4, and then I'll select these 2 and just change it quickly to 250 kilowatts. Okay. Each of these pipelines will be 5 meters in length. So we'll just make that 5. And we obviously know the design flow rate for the orifice plates from our hand calculation. So I'll turn the auto size feature on. We're going to size it on flow, and the unit will be kilograms per second. So let's just change that. Okay. So for the 370 kilowatt units, the design flow is 2.969. And for the 250 kilowatt units, it's 2.00609, just to be more accurate. Okay, so now we're ready to calculate the system. Now let's just look at this for a moment before we calculate. So from our heat exchanger loads, we were able to determine the mass flow rate which we have defined for each of these orifice plates. Now, if I go back to this pump, I could have selected size for flow under the automatic size feature, but it's important to be aware that because I have already set the design flow rate in the orifice plates, there's no need to define the flow because it's already defined across each lateral, so the total flow rate in this system has been defined already. So we can size it on duty pressure rise. If we didn't know the design pressure drop across the system, we could do the reverse. Okay, so let's calculate the system and see what happens. Okay, so we've got flow distribution throughout the system, and we've got a number of warnings, and we can look at the warning messages. We've got high pipe velocity warning. So let's look at this pipeline. Again, all pipes placed in the flow sheet were 2-inch by default, so let's just see what we've got here. We've sized them on economic velocity, which gives us a value of 1.25 from the value stored in the database for pipe sizing data. Okay, so we've got all our pipe materials down here, so we're using steel pipe, and you can see the various considerations that are included in the economic velocity calculation. The software uses the general equation to determine this exact economic size. So it takes into consideration energy cost, operating days per year, and so on. Now, the software is suggesting an exact size of 101, so approximately 4 inches pipe diameter. So I can now look at changing these 3 pipelines to 4-inch. Let's just see very quickly, 102 and 102 millimeters. Now, there's a number of different ways that I can multi-select these pipelines. I can select this top one holding the shift key, select the remaining 2, or I can go to the list tab, list the pipes, and I know that this is pipe -3, -23, and -5, so I can select -23, -5, and -3, and I'm just holding the control key to do that. And then access the pipes database, select my 4-inch pipe, schedule 40, recalculate to refresh, and now the pipe warnings have disappeared. And we've got 2 little warnings here for our T-junctions, and it's just to let us know that the K value, although has been calculated accurately by the software, it may be suspect, and because it's outside the range limitation for idle chick-T relationships. And that just means, based on experimental data, that the calculated value for K, the branch K and the straight K, may be outside the laboratory test data available, and we might need to check that. But there's further information in the help file on that and what is an acceptable K value for idle chick-Ts and Miller Ts and so on. And often you'll come across this warning when we have a T-junction with different sized T connections. So you might have a 2-inch pipe connection and the remaining 2 connections on the T might be 4-inch. So the software extrapolates the equations to determine the K value accurately. Okay, and all experimental data to date is based on equal sized pipe connections, hence the warning messages. Okay. So I can now look at my heat exchangers, and I can see the design condition in my rough hand calculation was a design temperature change across the heat exchanger of 30 degrees, and you can see now that the software is telling us that the inlet fluid temperature was 15 degrees C, which we had set down here, but the temperature or the heat energy change across the system gives us an outlet temperature of 45 degrees C. So you can see that's been applied now to this system. Okay, so that's a very quick auto sizing demonstration for you. What I'll show you now is the component, the new components bar feature. So if I select View, Component Bar, you can see this new component bar appears on the screen with all components that you have in your component bar displayed. So you can just very quickly pick and choose which component you need and drop it onto your flow sheet. And if you want to remove any of these, you just simply select the down arrow and add or remove buttons, and you check on or off the various icons that are relevant to your system. Okay. And then obviously you can hide the component palette and then you only use this one, or vice versa. Okay. Now the other new feature is the data report. So I can display the data report for this system, and all I did there was select, I'll do it again, View, data report, and we've got all the input information and results information here, so I can just scroll across to view the remaining information for the system. I can populate this for just the input information, just the results information, or the combination of both, and you can define it for all pipes and fittings, or only nodes and pipes. So this is just my pipes that's displayed, and I can scroll down. Okay, so that's another new neat little feature. Have we any questions at this point? Any questions?
Oh, I think you have just opened the muting section, right?
Jag ser här en dragonblock på Mikael. Någonting. Är det något som man gör med dragonblock och så sätter den sig själv?
Ja, man behöver inte ens följa det. Man kan sätta den mitt på den linjen. Eller mitt.
Hur den är grön?
Jag ska rätt upp där så lite flöden. Jag får liksom bekräfta systemet.
Anyone have any questions?
No. No. Yes, maybe when it has sunk in a little bit.
Do you find the new features of interest?
Yes, you have unmuted right now, right?
I've unmuted one or two people. Were still muted there, and I've unmuted everyone here now.
Okay, so I think it is everything is very much clear till now. It is going to be right when it is going to be released, this version?
February.
Oh, that's great. I think there is so many new features. Till now, I just seen each and everything is just new in this area, right?
Okay. Well, the webinar that you've just seen this morning will be available to download from our website, and also I will send you a little email of the PowerPoint overview at the very beginning, so you'll have that and you can always refer to it.
That's great. That's great.
But you know, if I'm not sure if you had signed in at the very start of the webinar, but if you want another one-to-one webinar session to go over any of the features you've seen today, you know, by all means, drop us an email and we'll arrange that for you. It's no problem.
Yes, definitely. If I'll find any problem, I'll just call to you or maybe mail to you, right?
Yeah, absolutely. Yeah, that obviously applies to everyone. Yeah.
Yes, thanks.
Yeah, no problem. Has anyone any questions or suggestions or anything they'd like to discuss?
As far as myself is concerned, everything is very clear right now.
Okay. Thank you. Anyone else?
No.
Are you happy enough? Are you happy? Good.
Can say.
One thing I'd just like to point out is, often features included in our software have been brought to our attention by customers and so on. So if, while you're using the software, you feel there's anything that should be added or you'd like to see added to the program that would help you in your daily work, please drop us an email and let us know, and we can look at including various features for you. Any more questions before we wrap up for today? No?
No.
Everyone's happy enough? Okay. Well, as I say, you can always contact us at support@fluidflowinfo.com, and we'll look forward to hearing from you. And thanks very much for signing in to today's webinar session. Okay.
Thank you very much.
Yeah.
Thanks very much, everyone.
Thank you.
Thank you. Bye-bye. Have a good day.
Bye.